So let's look at an example of using the limit comparison test. So here we have an integral, improper, from 3 to infinity, this rational expression. Now, the problem with using direct comparison is there's a lot going on here, right? I know that those lead terms are really what determines the long-run behavior. So out at infinity, this thing should behave like x cubed over x to the fifth, or just 1 over x squared. And we know what that integral does. The problem is I don't know if this is bigger or smaller than 1 over x squared, because if all these other terms are being added and subtracted, they're all having canceling effects on each other. I'm not sure what the inequality is or if it stays. So instead, that's perfect for limit comparison, because remember in the statement, there's no mention of f or g being bigger and smaller. It's just a matter of their growth rates being the same. So remember, what you want to compare with is totally determined by those lead terms. So we're really looking at x cubed over x to the fifth is the thing we'd like to compare with, or 1 over x squared. And we already know what that integral does from our fact that we proved earlier. So all we have to do is establish that that limit's a constant bigger than 0, and we have it. So first of all, you don't have to prove this, but I want you to state, whenever you're using a theorem, state that the conditions are met. So first of all, f and g have to be positive and continuous. So the first thing I want you to mention is that both 1 over x squared, the thing we're going to compare with, and our integrand there, x cubed minus x plus 2 over x to the fifth plus x to the fourth minus x cubed, those guys are positive and continuous on the interval that we're looking at, from 3 to infinity. You need to convince yourself of that. You don't have to prove it for me. But this, I want you to state, because it reminds you that certain things have to be true first, and it shows me that you understand that. Next, we're going to evaluate that limit. Now, it doesn't matter who goes on top or who goes on bottom, because if you end up with a number, say 15, if you had it flipped, it'd be 1/15. Both numbers are still numbers bigger than 0, less than infinity. So you can't really go wrong. I'm going to put I usually put the thing that we're comparing with on the bottom, though. So let's look at the limit as x goes to infinity of x cubed minus x plus 2 over x to the fifth plus x to the fourth minus x cubed, all over 1 over x squared. So if we flip that and multiply through the x squared, we have x to the fifth minus x cubed plus 2x squared over x to the fifth plus x to the fourth minus x cubed. Notice we end up with a rational expression of like degrees, which we would expect because we wanted to compare with something with the same growth rate. So now remember, these are indeterminate, but we use our little algebra trick. Divide top and bottom by that largest degree. And we have the limit as x goes to infinity of 1 minus 1 over x squared plus 2 over x cubed over 1 plus 1 over x minus 1 over x squared. And so as x goes to infinity, that's just 1 over 1, or 1. And we wanted to show that that limit was some number bigger than 0, less than infinity. So I'd like you to say that. That shows me that that's what we needed. We needed that number to come out to be bigger than 0. And we need to know, why do we know the thing that we compare with converges? Remember, we proved already that the integral from 3 to infinity of 1 over x squared dx converges because p is 2, which is bigger than 1. All rests on that power. So that tells us the integral from 3 to infinity here that we were wanting to know about is also convergent by LCT. So when you make this argument, I want to see a couple of things. I want to see you state that the conditions are met, reminding us all what those conditions are and that we know them. Evaluate your limit. The key thing is that that be a number greater than 0, which it is. And then state that what you know about the thing we compared with. And that was our special case there. We know that stuff 1 over x to the p converges if p is bigger than 1. I want to see all that. That shows me that you are clear on what that decision is. And then your conclusion that the integral converges by LCT. Avoid using pronouns like it converges, because that converges and that converges, and the convergence of this implies the convergence of that. So try and avoid pronouns. Whenever you're talking about something converging or diverging, state precisely what integral you're talking about. This will become even more important later on when we look at series. We'll have multiple things going on. You should be as explicit as possible when you're making your conclusions.